is discharge. So you see these squares here. This is a discharge record. Discharge in millimeters per day, measured as function of time. And so in hydrology, we do a lot of different things, one of which, surface hydrology, people want to predict this time series. So they build models to do so. Let me see if I have one of these models here. So you get an idea what type of model that, yeah, here, for instance, these two arrows, don't look at that, but these are so-called conceptual models. You measure precipitation, and then you have a number of different reservoirs with fluxes between those reservoirs. And then each of these reservoirs produces an outlet flux. If you sum up those outlet fluxes, you get your inflow in your river. And if you then route that inflow, then you get your QT is your discharge simulation prediction at time t. So based on precipitation, and this arrow should be the other way around, but that should be revised currently. And based on evaporation, actual potential evaporation depends on the model. Based on those two inputs as function of time, you produce your simulated discharge. And for that, you use this conceptual model, and a conceptual model has a lot of parameters. And those you're estimating from that time series. That's how it essentially works. Let me see where we are here. Here, so you use these measured time series, and you see this black line. That is the maximum likelihood fit of the model. That's the best you can do after using, in this case, I call it maximum likelihood, but we use Bayesian inference, but we use a uniform prior. So essentially it's the same thing. Now, some people say, so people have done this for many years, okay? But still, operationally, people don't use this very much. There are, at least I believe in the US, 4,000 locations, rivers, where they forecast stream flow. And over the years, a lot of these methods have developed. And in operational settings, they don't really use these, what they call statistical methods very much. Because when you're applied, an applied hydrologist, a field hydrologist will say, yeah, these are all fancy techniques, but I don't believe that a statistical metric of fit between simulated and measured discharge, simulated measure gives me the best possible forecast. So someone in the field may say, you know what, when I calibrate a model, I don't necessarily care about maximizing my likelihood. I care about getting the peak volume right. I care about getting the base flow right. So essentially, they look at so-called signatures of this discharge time series, hydrologic signatures. And what they call one of those signatures is the flow duration curve. Essentially, the flow duration curve is just the CDF of the data. So if you make the CDF, cumulative distribution function of your data, that is the flow duration curve. Okay? Now, so I was always working on these techniques, all these Bayesian methods, statistics, and suddenly I realized, okay, my goal was always, can we develop Bayesian methods in such a way that people can use what they call hydrologic signatures? Because all those don't satisfy statistical principles, right? So meaning assumptions about least squares or distribution of residuals, all that. So that's how I got to the scoring rule. So point is that continuous rank probability score, that's one strictly proper scoring rule. You can turn that into you can use the flow duration curve here. I think here, yeah, here's a flow duration curve. You see the red is from the data. And then gray is simulated by a model just using Monte Carlo simulation. And red is the solution that you get when you maximize that continuous rank probability score, which I now call flow duration score or so. And the Blue is what you will get if you do maximum likelihood. So you just use the discharge data and you fit using Bayesian methods, random walk metropolis algorithm. You get a posterior, you find your peak of your posterior, then this is the flow duration curve of the peak of the posterior. And this is the point why hydrologists don't use statistical methods, because they will say that this diverges too much from the measured flow duration curve. So we may create least squares predictions, but with a model that for a field hydrologist not necessarily makes physical sense at all times. So the first point of this is how I got to that sandwich stuff that I'll present soon is I started looking to scoring rules. So while working on this, so we can turn this flow duration curve into a strictly proper scoring rule, and that we can use for Bayesian inference. That's what's done here. So nice, okay. While looking into that theory, I suddenly came across that, because the next step, what I want to do is now, in this case, it's all evaluation. Okay, there's no calibration going on in this example here. I just sampled the parameter space. You see the 50 best simulations here, according to that flow duration, strictly proper score. Those are all plotted here. This is the best according to maximum likelihood. The red is the best among those 50 members. There's no calibration going on, because the next step is to use that flow duration scoring rule and then do Bayesian inference. The problem with that is, and that's how I got to the next step, what I'll present, and that is that the asymptotic distribution of a scoring rule is not what is called the naive variance, the Hessian, the inverse Hessian. No, that is the sandwich distribution. So when I read that, was, what is the sandwich here? The sandwich variance. And that led to a whole new paper, and that's what I'm talking about next. And this has a lot of implications. Essentially, when we do inference, everyone almost in this world makes the implicit assumption that your model is correctly specified. Your likelihood is correctly specified, genuine. And we almost always know that that's not true. Yet we keep using theory as if the model is correctly specified. There's all beautiful theory associated with that. And we already know it's not true. So this paper is showing that if you relax that assumption that your model may be misspecified, I use model and likelihood interchangeably because it's the same thing. But if you let that go, then things are different and you get very counterintuitive results, insights. Very few highlights that under misspecification, your fundamental currency of data informativeness is not the feature information, but it's the Codembe information. And I'll show next what that is. That the asymptotically valid sandwich variance, if you use that you get substantially larger uncertainties in your parameters. Now, in applied fields, particularly hydrology, there are a lot of users of what's called the clue method. What I'll show is that is based on a fundamental misconception. And that is, what do people do? When they apply Bayesian inference to a misspecified model, there are essentially two things you can do. The first thing is you inflate your sigma square, your variance of your measurement errors, so that it includes model error. That's what clue does. But it makes that sigma square so large that there's no theory for that. It's all subjective. And the way you can do that is, second way you can do that is by raising your likelihood to a power, an arbitrary power, or you multiply your log likelihood with the power. And I will show that under misspecification, your parameter uncertainty is invariant to a likelihood power. That's very non-intuitive. You would think if I have a likelihood and I square that likelihood, that your posterior gets narrower, 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 right? Higher confidence in your parameters. But that's not true. Then MC methods, whatever you see in the literature, will be that whatever posteriors they give, that is not the correct posterior. So that includes a lot of my own past work as well. Those are correct posteriors under the assumption that your model is correctly specified. And we know that that's not true. So again, if your model is not correctly specified, those posteriors usually are much more dispersed. Now, and in this paper, I use something that we call distribution adaptive likelihoods, and I will quickly, briefly address and show that if you use distribution adaptive likelihoods, that you will reduce what is called information bias. Now, let me go to, so you have to understand a few. I'm not a statistician. I'm not a mathematician. I'm not a physicist. I do have colleagues that are all that I talk to. I just got off the phone with a colleague of mine that is now working on a lot of stuff that I was working on because we're really close to really big fundamental steps forward. So I've got a bunch of people very excited about all this. They are statisticians, physicists, mathematicians, really good at what they do. I understand quite a bit, but I don't have my degree in math or statistics, okay? So keep that in mind. Now, M estimation is one of these things that very few people have heard of. That's a whole field. Okay, M estimation is a generalization of maximum likelihood and least squares estimation to situations in which the data has outliers, extreme observations, and or does not follow a normal distribution. I recommend you read about John Wilder Tuckey. Unfortunately, he passed away quite a few years ago, but basically he realized very early on that the standard statistical methods that we use still today are really prone to outliers and other things, meaning the inferences they provide are extremely sensitive to assumptions that are not met. So he and a few others started the field what's now known as M estimation, where they try to build estimators that are more robust. That's why M estimation is also called robust estimation. Okay, so parameter estimates, theta is my parameter, and that's a parameter in one of these models. Could be any model, but just theta is a vector. And they generalize maximum likelihood estimation to some function of the standardized residuals. E is my residual. And when I use an underline, that means it's standardized. Okay? And we don't use this in hydrology. Now, in high school, we all learned that if you want to find the minimum or a maximum of a function, you set the derivative to 0, right? Now, that's how you find the optimum parameter values. We call this the gradient vector. This is a vector. I use the numerator layout in gradient, so that's a vertical vector, d by 1. We have d parameters, so that's a d by 1 vector. And you try to find where are all those equal to 0. That's how you find your optimum. Now, I don't do very much with M estimation per se in this paper, only one aspect about M estimation, but I talk about it here because this has a lot of implications also for work that people have done on estimation in hydrology. So here are a few M estimators, okay? You may recognize some of them. So loss function, influence function, and so-called weight function. They're defined above. And here you see different estimators that you can use instead of a least squares estimator because they're more robust against outliers. So you see here that you have the actual, if you take the derivative of your rho function, then you can define so-called influence function, and you can define a weight function. Influence function tells you what is the influence of a residual of a certain magnitude on your cost function. Okay, and you want that to go to 0 essentially. And you see that with the least squares estimator, where are we? Least squares here. This is the least squares estimator, that weight function does not go to 0. Meaning that outliers will still influence your loss function. And there are estimators where that's not the case. You see here that asymptotically go to 0, or they have what's called a rejection point. Anyway, I just thought I'd point this out. When you look at MS2, I'm sure you can figure all this out yourself. What I'm interested in is one aspect, and that is a paper that Taki wrote in 1967, and that is about robust standard errors. So when you have all these estimators, you want to know what is their asymptotic distribution. And that's where the sandwich variance comes in. So under misspecification, I'll show that next, your asymptotic distribution is not what we always thought. Some notation stuff. Oh yeah, here, definitions maybe, likelihood. Single observation is omega. I use omega for observation. I know that there's in measure theory that, anyway, we can discuss the notation. I want to keep it as simple as possible. The score function is the first derivative of the likelihood function. Then we have a Jacobian matrix. Essentially, that is your score function here for each individual value of omega, because in a time series, we have an omega 1, an omega 2, an omega 3, all the way up to omega n. So it's an n by d matrix and the Hessian matrix. Then we have a sensitivity matrix, that is minus the Hessian. Then we have a variability matrix, which is the vector outer product of your score function. Okay. Then we have the Fisher information matrix. That is negative your Hessian. And then we have what's called the Codembe information. And that is what we call a sandwich. And why is it called a sandwich? This is a bread matrix. And this is a meat matrix. So you have bread, meat, bread. That's why it's called sandwich. Okay. Now, here's all the theory, maximum likelihood, etc. I mean, we can talk about this if you want, but this is just the standard theory. And if you follow that through, then this is your Codembe information. Okay. Now, asymptotic behavior, you can look at all this. I'm still fixing the notation with p limits and all that, but it's almost done. So there's a number of things that are going to change here. But there's an important point here. Let's make the assumption that our likelihood is correctly specified. Essentially, when you then follow all the theory, what you will see that under a correctly specified likelihood, you satisfy what's called the second Bartlett or information identity. And that is that the expectation of the second derivative of your log likelihood is equal to negative the variance of the score function. That is true under a correctly specified likelihood. Meaning that your Hessian matrix is equal to, and we call this the sensitivity matrix, this thing, the sensitivity matrix and the Hessian matrix are equivalent to each other. That is true when your likelihood is correctly specified. If you then go back to that Codembe information, and you know that this one and this one are equal to each other, then this will create an identity matrix. And that's how you get to your Fisher. So then under a correctly specified likelihood, the limiting distribution, the variance of your maximum likelihood parameter estimates is the inverse of your Fisher information matrix. That's what we always apply. Now, and then you can construct confidence regions, confidence intervals, all that stuff. Okay, you can then also show under a correctly specified likelihood function, information or the feature information of n data points is equal to n times the feature information of one data point. Now, that's what we learned. At least that's what I learned. Yet, there is theory for a misspecified likelihood. Here's an example, very simple, basic example. Imagine that I have a data generating process, which is just a standard normal distribution. So I just draw samples from a standard normal distribution. Here you see the samples, the red dots. Now I assume a uniform distribution as my model. I find the maximum likelihood estimates, minimum of the distribution, and the maximum of the distribution. Now, what do we see? Few things. My data generating process was standard normal. That has two parameters. Mean, variance. Mean of 0, variance of 1. Misspecified model, minimum, maximum. So first place, that if you use a misspecified model, we know all this, but I'm pointing out, is that the A and the B have nothing to do with the mean and the variance of my data generating process. It's a different subspace. So that's the first important thing to think about, is that when your model is misspecified, the parameters that you're estimating have nothing to do, so to say, with the parameters of the data generating process. Okay? Now, then the question is, what am I estimating under misspecification then? Now, you can show that under misspecification that you're minimizing the Kullback-Leibler divergence between the unknown data generating process and your misspecified model. You're minimizing that Kullback-Leibler divergence. Okay, that's a technicality. It's important, but I'm interested in primarily parameter uncertainty. Now, under misspecification, this second Bartlett identity is no longer true, meaning that the expectation is now not with respect to theta, but it's with respect to Q. Q is the distribution of the data generating process. And that identity no longer holds, meaning A1 and B1 are no longer the same. The sensitivity and variability matrices are no longer giving you the same answer, or they're not the same, they will not have the same values. So if you now, in a correctly specified theory, this produces an identity matrix, but if it's misspecified, that's not giving you an identity matrix. It gives you the sandwich estimator, and that's the paper of Huber, 1967. Gives you rise to what they call robust variance sandwich estimator, okay? Which is the inverse of the Kodembe information. So this is your sandwich variance. And the Fisher variance is called the naive variance, okay? Now, some caveats here. We cannot determine the matrices because we don't know the the parameters of the data generating process. Anyway, you rely on maximum likelihood. If it's consistent, all that, you use the maximum likelihood estimates, and that's all okay. Second, I work on time series that are dependent. So, meaning the independence assumption of those data points is not valid. So how do we account for that in all this theory? Now, there's some corrections. For instance, under misspecification, then this becomes your sandwich estimator. Lots of linear algebra. This is a weight matrix, and this is your estimator of your variability matrix with dependence among your realizations. Now, and then you can go to Newey and West, and this is all worked out how you can determine that. Essentially, when your model is misspecified, you're going to see that the score function, the first derivative of the log likelihood, that those entries are correlated with each other in time. And you need to account for that in your variance estimator here, in this thing, because B essentially is a variance matrix of your score function, of your gradients. So you can account for that by taking the lagged covariances, essentially. So you get consistent estimators. Now, okay. Now, also, I work on cases where the number of estimating equations is equal to the number of parameters. In that case, WD is inconsequential. Whatever you choose, you can show it drops out. So under misspecification, this is our sandwich estimator, where this is the Newey-West correction, which gives us a consistent estimator of the variances of the score functions if the score functions are autocorrelated. If you create an AR1 process, right, you have a variance of the partial residual, you have a variance of the past. Now, that's the way to separate those, to remove the covariance from your variance. Now, case studies. So what I did to illustrate all this, I thought, okay, I need to do some academic demonstration of how this works. So I went to soil water infiltration. Soil water, this is what John Phillip had done. Very smart guy, worked in Australia, brilliant guy. He actually ran under a tram in Amsterdam, across from a bar where I drank a lot of beer. I wasn't there at that time, but he was a very smart guy, and I never met the guy, but apparently people thought he was very arrogant, but he was very bright. But anyway, what he showed, that how I can simulate or predict cumulative infiltration in the soil as function of time. That is essentially a polynomial function, okay? And where if you restrict attention to the first two terms, then the first A, the A1 is what's called the sorptivity. And that second term is a multiple C, which I assume 1 from convenience, doesn't really matter. And the second is the saturated hydraulic conductivity. S and Ks are soil parameters, okay? Each soil has its own Ks value. So these are measurable in the lab, in principle. Sorptivity is a time variant parameter because it depends on moisture content, okay? Now, but this is nice because this is linear regression. So I can do everything analytically, right? I can compute the naive variance, I compute the sandwich variance, I can compare, etc. Now, so I write that in matrix algebra. This is my residual. I make the assumption that I have a perfect model, say, though the residuals behave as the measurement errors of my omegas. Now I can do minimization using a least squares approach with the constraint that my parameters S and Ks need to be larger than 0. Sorptivity cannot be negative and saturated hydraulic conductivity cannot be negative. Anyway, usually you don't need to do box constraint minimization and you have your least square solution here, standard theory. And if your S or Ks is negative, then you need to do box constraint to make sure that doesn't happen. Okay, now, so give me a time series of cumulative infiltration data. I can tell you what S and Ks are. Okay, now we want to go to Bayesian theory. So I specify also, so that's why this first step, here's my likelihood function, because here it's my weighted sum of squared residuals. Now I want it's more than I guess frequentist or least squares type description. I want to go to a Bayesian description. I use what's called simply a normal likelihood function. Okay. And now what I do, this is important, I use what's called a power likelihood. Okay. I have a power here, lambda. I raise my likelihood, this one, to a power lambda, and lambda is positive. Okay. I call this the normal power, and this is the log likelihood. So if this is the log, right, and this gets in front, so that's why you see here that the normal power log likelihood is lambda times the normal log likelihood. Here it is. Okay. Now I want to compute what is the naive variance, right? I have my equation here. So now I can derive the score function, the first derivative. Here it is. Here's the solution for your first derivative, where this is the variance. Sigma epsilon squared is the measurement error variance. This is your design matrix. These are your measured values, n by 1, design matrix, parameter vector. So this is n by p, and this is p by 1. Or I think in this paper I call it d. So this is n by d. This is d by 1. Now, then you can derive your Hessian. That's the second derivative. Now, here is your Hessian. Okay? Now I want to compute my variability matrix analytically. Now, I work that out here. Here I have my variability matrix. But I still have my theta in here. I have an expectation here. So for my MAP parameter values for theta n hat, this difference should be sigma square epsilon. So if you work that out, that means that for your maximum likelihood parameter values, your variability matrix is equal to this. So here's a summary that for your maximum likelihood parameter values, your sensitivity matrix is this, and this is your variability matrix. Now I can enter those in my naive variance estimate and in my sandwich variance. Now my naive was the inverse of the Fisher information, right? Gives me this. My sandwich was this product. And look what happened. My sandwich is independent of lambda. So that power that I use in my log likelihood is gone. And whereas your naive variance is there. So in other words, if you would use, I'll show that next. Here is some result here. Naive estimator. This is the uncertainty in S and KS when you assume your model is correctly specified. And that's the confidence region you get at 99%, 95, 90, and 50. This is your maximum likelihood solution. This is synthetic data. I created this data myself, okay? That's the naive estimator. That's what we always compute. This is your correct uncertainty. Even though this is, and so what's happening here? In the inference, I use a value of lambda, where is it here? 0.1. That's what I use in this inference. So what I did is I set lambda equal to 0.1. You saw that in the naive estimator, we did 1 over lambda times the variance. Whereas in the sandwich estimator, that is not sensitive to whatever, that's not sensitive to your lambda value. That's why you see a difference. It's the same data. This is solely the effect of your lambda. But now you wonder, when I change that lambda to 0.1, why is my naive variance this? Why is my sandwich this? So let's do some other methods. I use MCMC. And what do you see? That MCMC methods, Bayesian methods, give you the naive estimates. Whereas the bootstrap method gives you the sandwich estimate. So this is really strange, right? Frequentist and Bayesian methods are supposed to give you the same answer, certainly when n goes to infinity. Prior, yeah, who cares about a prior? But they don't give you the same answer. And this is the state of the art, okay? There is an inconsistency here between both methods. We're trying to reconcile this. That obviously needs theory. That's why I was just talking to my colleague for an hour, because we finally made big steps forward. But this just to show that when you use a lambda value in your likelihood function, and why would you do that? You would raise your likelihood to a power smaller than 1 if you want to temper learning. It makes your posterior more diffuse, right? When you use a lambda value smaller than 1, you raise your likelihood to a power less than 1, between 0 and 1. You're trying to temper learning. You try to make the prior more important relative to your likelihood. And these results show that indeed the naive variance suggests that lambda has effect on your uncertainty, on your confidence regions, whereas the sandwich says, yeah, you can raise to whatever power you want your likelihood. It's not going to change your parameter uncertainty. It's very counterintuitive. Now, then I wanted to do an example with a state variable. So I went to the ABC model. It's a hydrologic model, very simple. We have precipitation. Part of precipitation is evaporation. Part of precipitation is infiltration. Part of precipitation is surface runoff. And then the water that infiltrates goes into a groundwater reservoir, and that has a state variable R. The groundwater reservoir produces base flow, and the sum of the surface runoff and the base flow is the stream flow. So you can solve this easily with second order, third order, whatever, adaptive time stepping methods. So you get very accurate stream flow simulation. Now, I also want to derive my sensitivity matrix, my variability matrix, my Hessian, all those matrices score function analytically. So I won't go over that, but if you write out your normal power likelihood here, it's the same as previously, but now I have a much more complex model here. Now, much more complex, slightly more complex, but I need to derive those. Now, it's all done in the appendix. I can quickly, here. This is the ABC model here, where this is stream flow at time t is 1 minus A minus B times precipitation at times t, plus another coefficient C times groundwater storage at the previous time. Like, it's not clear as that the previous day, the previous hour. I work with a daily time step, or not time step, daily data. So I assume it's the previous day. And you see that groundwater storage at time previous day is C prime, and C prime is 1 minus C times the groundwater storage of the day prior, plus A times the precipitation of yesterday. Now, if you write this recursion multiple times, you can write it as this, and you can keep doing this. I wrote a MATLAB script that does all this automatically. If you want to do this 30 times, it will do it 30 times, and then you can insert this equation here for your stream flow at time t into your likelihood here, and then you can take derivatives with respect to A, B, and C. Okay, and you get all these formulations here. So this is the gradient with respect to A. Yeah, you get this formulation. This is the gradient with respect to B. This is the gradient with respect to C. And now, if I take another derivative with respect to A, B, and C, I get my Hessian, or variability matrix if I take the outer product. So you can work all this out. You get really long equations. And this is only with 5 times, when I go back 5 days. If you go back 30 days, these equations get really long, but it's all very straightforward math, okay? So now you have these matrices. And now what I can do, I can just interpret what happens when it's misspecified and when it's not misspecified, because that's what I'm trying to show. And I'll show you these matrices. Here it is. So the first thing I do is the ideal case. What you see is your sensitivity and your variability matrices are the same. So what I do is I use the ABC model, I generate the simulation, I perturb those simulated value with the measurement error, and I say, that is my measured record. Then I do maximum likelihood. I find the maximum likelihood parameters, and at the maximum likelihood parameters, I determine the A and the B matrices. Sensitivity, variability. If the and so they should be equal to each other, because the only errors that I introduced here are random measurement errors on the discharge. I use the same model, so you see that's the case. These matrices are identical. And why are they not exactly identical? Because I use my analytic estimator here, but I only go back 5 times. I should go back further back in time to get the sensitivities with respect to A and C correct. But if you do this numerically, you will see that the A and B are identical. Now what I do is the semi-ideal case. I use the measured discharge record as in this table, but now I perturb the rainfall that goes in my simulation model. I just add 25% error. So I have 5 years of record, daily data, daily discharge, daily precipitation, and I just add plus or minus 25% within that interval. So uniform numbers, and then I perturb the rainfall. So the rainfall that was used to create my measure data is different than the rainfall I used to do inference with, to estimate the parameters. Now here's the effect. This is the A matrix, and this is your B matrix now. And this is the Newey West. When you're now going to have autocorrelation between your score functions, so you need to count for that. So this is the one you're supposed to use, but this is the one without that adjustment. So what do we see now? That these two matrices are no longer the same because you have a misspecified model. Because the rainfall, yeah, I mean, the model is, that's the question. But it is misspecification. We perturb the rainfall. We're using the wrong rainfall now. And you see what the effect is on A and B. Now, if you work that out, I can look at the univariate distribution. Then this is the naive distribution. And this is the sandwich distribution. So that's really, these differences are small, but this is only a 25% error in rainfall. We're using the correct model, okay? Everything else is still correct. It's only rainfall. You already see it has an effect. And here you see, if I look at the confidence regions, naive, the dots are MCMC. So I have the naive estimator from the frequentist approach. I have my MCMC approach. You see that they're identical, 95%. And this is the sandwich estimator. This is the correct result. A, B, A, C, B, and C. Now what I can do, I can go to a real model. I can make it more complex. This is all toy stuff, wonderful, but we want to do better. So what I did is I went back to a paper I published a few years ago. This was sitting on my desk for 8 or 9 years already. And it was just sitting there, and I thought it's time to submit. So what do I do in this paper? This builds further on work that Gerrit Schoeps did at the TU Delft. And we are looking for likelihood functions that not necessarily assume that the residuals are normally distributed. We want to generalize that. So we call that distribution adaptive likelihoods. And so what are distribution adaptive likelihoods? Are likelihoods that have nuisance variables, beta, xi, and that allow for all these different distributions. So this was Gerrit's contribution in 2010. We wrote a paper. He came up with this idea. And this paper extends that further, plus it corrects a flaw in that first paper, a small, mistake. Gerrit doesn't like it when I call it a mistake. But in all honesty, I think it's a little mistake. That has to do how you do variance treatment, whether you do variance treatment of the residuals before variance stabilization. You should first stabilize the variance and then do treatment of autocorrelation. Anyway, so that's rectified here. Plus in this paper, I developed what's called the universal likelihood function. It's a further extension where you're even more flexible. So now we have a likelihood function that has all these nuisance variables that you can estimate along with your model parameters. So where you no longer make the assumption that your residuals are normal, can have any distribution. Now, I wanted to know, in this paper, I test a lot of these likelihoods in a table here. This is for real data. I test all kind of formulations of these different likelihoods, and I compute different scoring rules. And what I was now interested in, if I go to the maximum likelihood solution, use uniform prior, and I compute the A and the B matrix, or the A and the beta matrix, Newey-West correction, are they going to be the same? Now, so that's what I do here. I introduce these likelihoods first, some of which use an AR1 or AR2 correction as well. So here are these different likelihoods. Here it's a presentation again, all the shapes that they can attain. I use the same model, and here. This is for one of these likelihoods. Universal likelihood with eta, that was, I called that lambda in the other paper, but lambda is used for learning rate, so I had to relabel. Anyway, point is, I use phi1, first order autocorrelation I allow for, and I believe eta is the kurtosis or so you can play with. Now, look at A and B. They're an order of magnitude different. And you see here, I present here for normalized parameter values. All the parameter values are normalized between 0 and 1. Otherwise, I cannot compare these two matrices because one parameter that ranges between 0 and 1,000 is going to dominate. So I scaled all the parameters to be between 0 and 1. But you see an order of difference, magnitude difference between beta and A, and they should be the same. So it's nice to use a distribution adaptive likelihood. You may better describe the residuals, but if you look at the maximum a posteriori density or maximum likelihood solution, A and B are very different, meaning that second Bartlett condition doesn't hold, and you have a sandwich variance. Now, so here I show the results where for three different likelihoods, those distribution adaptive and the normal likelihood. This is the naive estimator of your uncertainty. This is what MCMC also gives you, approximately. And this is the sandwich estimator. And you see that the parameter uncertainty, again, we are 10 negative 5, here it's 10 negative 4. That does make a big difference. And these are numbers. So here I show the marginal distribution of that universal likelihood, one variant, under assumption it's correctly specified. Then this is the frequentist estimate of your marginal distribution. You see the blue bars are the MCMC approximation. The green is the sandwich estimator. And then the green bars are a sandwich adjustment of your MCMC samples. I will briefly talk about that next. You can adjust your posterior samples. You can do a sandwich adjustment. There's different ways you can do that, but here if we look at the bivariate, here, you see the differences are getting large. I mean, this is becoming significant, and the point is, people have always done stuff like this, but it's all subjective. They inflate uncertainty in the parameters to avoid overconditioning, that your credible regions don't match. But if you apply the sandwich variance, your parameter uncertainty would become much larger because it accounts for that misspecification. A and B matrix are not the same. They don't produce an identity matrix. Now, blue, that again is MCMC. Blue line, the blue dots are MCMC. That's 95%. The blue line is from the sandwich or the naive estimator from your Hessian. That's inverse Fisher, right? Then the green line is your sandwich, and then the green dots, that's your MCMC adjusted samples. Now, here you see the difference in, if you now simulate, this is 90, 50%, 70%, and then you have 90 and 99%, and this is with the sandwich. You see you have significantly increased uncertainty intervals of your discharge here. Just the effect of the sandwich estimator. Now, So what's the point here? Under misspecification, your posterior distribution is the naive variance. It should be the sandwich variance. That's a fundamental problem. MCMC methods, the random walk metropolis algorithm, converges to the wrong distribution. Okay? Maximum likelihood theory gives you the naive variance. It should be the sandwich variance. But how can we make all this consistent? When I want to use MCMC or any other method, I want it to automatically figure out there is misspecification going on, and then I want it to figure out that it should become a sandwich variance. I don't have to worry about that. As it stands right now, MCMC methods will give you the naive variance. So this paper is, we're not diving deeper into MCMC here, but that's why my conversation was with my colleague. I think we now figured out how we can do a theoretical correction of the MCMC theory so that you will get the sandwich variance under misspecification. Now, there are different approaches in the literature, but they're all ad hoc. And they're all in two steps. First step, you run an MCMC method, a sampling method. You get the optimum and the naive variance from that. Then at the optimum, you compute your variability and sensitivity matrix. You compute your sandwich variance. And then you do a correction, K. You can look at this as, they call this an omnibus scalar, K. That's going to be between 0 and 1. And now you do another MCMC run where you multiply your log likelihood with this K value. And then you get the sandwich variance, okay? And what you see, that if you apply this theory to our first case study, then it says that you should multiply with 1 over the lambda we used. Now, if you do that, then you will see that that learning rate cancels and that you indeed get your normal likelihood as it should have been. So this all works beautifully, but only in situations that you have a really perfect, nicely quadratic approximation. Now, if I compute that K value for our case studies, the last case study, you get K values very close to 0 for those different likelihoods, meaning the model is severely misspecified because the K value should be 1 for the correctly specified model. Those two matrices, this will produce an identity matrix. If your model is correctly specified, then the trace of an identity matrix, that is D by D. Then you take the sum of the diagonal elements. Now you have D elements. Now identity matrix, all ones, so you get D times 1. So you get D divided by D, K is 1. So if your model is correctly specified, K is 1. If your model is not correctly specified, misspecified, K will be closer to 0. Okay? Now, so you see, you get pretty close to 0. So what I did now, I tabulate here all kind of different formulations of those likelihoods, those distribution adaptive likelihoods. I compute their maximum log likelihood and I compute the K value. And what do you see? The gray highlighted ones are the ones that I studied and that I highlighted in the previous paper, that I showed results for in the previous paper. Even though I computed all of those in the previous paper as well, I only showed results for 3 of those. But you see that you do have formulations that have a K value that is substantially larger. And that was the point about distribution adaptive likelihoods being able to, they call that information bias. When the A and the B matrix are not identical, that's called information bias. Okay? Now, and so you can minimize information bias by using those likelihoods. But there's one caveat still here. And that is, why can this be so large then, 0.6, that it's relatively close to 1? When we know our model is quite misspecified, we have measurement errors in rainfall, we have all these things. And that is the other, thing we do wrong in my view. When we apply maximum likelihood theory, we always inflate sigma squared. We use for the measurement error variance of our target data, we always replace that with the variance of the residuals. That way you significantly inflate your confidence regions. That's a standard technique. That's done in these likelihoods as well to make it statistically everything coherent. When you compute partial residuals, they should have a variance of 1 to get everything, or the standardized residual should have a variance of 1. Then you can compute what is the variance of your partial residuals. Anyway, I don't want to go too technical. The point is, if you would use sigma square equal to the measurement error of discharge, likely your all these k values would be much closer to 0. But then you need to do another correction, and I'm working on that next. Then you need to use what's called the power likelihood. So that was already in here, that lambda. So you have two different approaches in the literature in general. Either you use a much larger value from sigma square to get the right uncertainty, right? So you inflate sigma square. We always do that. That sigma square in maximum likelihood is always replaced by the variance of the MAP residuals. Because you have measurement errors of your data on top of that model error, so you use a much larger sigma square. That's one approach. The second approach is you set sigma square to the measurement error of your data, as it should be, but you use a power likelihood to temper learning. So then the question is, how do I then infer that power likelihood? That is what we're working on now. And some technical stories on how to correct MCMC so that it automatically gives you the right variance. Always the sandwich variance. So there are different adjustment procedures. All of this is rather ad hoc, okay? So essentially it's 1 o'clock. I don't want to go further, but essentially that is what this work is about, is informing people that, hey, if you relax the assumption that your model is correctly specified, you're ending up in a different world with counterintuitive things. There is theory for that, but now we run into problems that methods that we use every single day are not producing asymptotically correct estimates. And that's how I got to that from the scoring rules, because the asymptotic distribution of the scoring rule is not the inverse Fisher, it's the inverse Codembe information. And that's where the sandwich comes in. So this obviously applies to lots of work. And M estimation is not used in many fields, but it has been out there since the 60s and 70s. So have a look at it, take it to your advantage, and hopefully it's useful.
Thanks, Jasper. That was awesome.
You're welcome.
I especially like the example with additive versus multiplicative noise, because I think Vince will definitely use that in his future work. I had a question about so your first example looked at the flow duration curve, and you're talking about how hydrologists care more about this than fitting the actual flows or whatever. So in that part, it seems more like a subjective choice. And then you go on to talk about model misspecification, where you have an objective difference between you think it's normally distributed, but it's actually uniformly, or vice versa. So what's the connection between that subjective choice of what we care about and the objective model misspecification stuff?
Yeah, so in this example, people try to use metrics other than statistical metrics, as you said. And the connection is that we want to know the correct asymptotic distribution. Whatever metric you use, you need to get your inference method should give you the right uncertainty estimate and the misspecification. And both of which is the sandwich. So in the case of the scoring rules, their asymptotic distribution is the sandwich. And why is that? Because when you use a scoring rule, there's always information loss. A scoring rule, a strictly proper scoring rule, is a likelihood, but with an affine transformation. So you can write n times the scoring rule value plus another, or n times the scoring rule plus a constant, that is equal to the log likelihood. And you have infinite n slopes and intercepts that will satisfy that. That's one reason. So the point is in the misspecification here. And so what I'm looking for are statistical methods, inference methods, where an hydrologist can use any scoring rule they want, and they get the right asymptotic variance, and it's the same under misspecification. So if you use a model, we always know that our models are misspecified. Whether your model is misspecified, whether your metric is incomplete, we should get the right answers. And as it stands right now, we don't. And so that's why I'm trying to develop theory that whatever metric you use, whatever model you use, that you get all the right results. You get, for instance, next paper I show that lambda you can infer, and that lambda, that learning rate is a measure of the degree of misspecification. It took me 25, 30 years to get to that. Not the log likelihood, that is a sufficient statistic of the degree of misspecification, that learning rate thing. Completely consistent. So under misspecification, when we know that the residuals can have any distribution for all kinds of reasons, how can we get an objective measure that tells us how misspecified our model is? That's that lambda. But that sandwich comes back as soon as you have misspecification of your incomplete information, a metric, an estimator, they have the sandwich distribution.
But I thought the amount of misspecification would be K, right? Or is it lambda?
Yeah, if K is close, yeah, K and lambda are the same thing, essentially.
Oh, okay.
They ultimately end up doing the same thing. K is measured, K is derived after the fact, whereas lambda is used during estimation. But ultimately, this is a problem also. It's a good point, because in different fields, they use different symbols, but ultimately it has the same effect. And you know, the interesting thing, just to show to you, maybe that gives an additional insight, that in that essentially that lambda, that allows you to relax that Bartlett condition. I think it's somewhere here in the paper where I, very simple example, so that if you multiply your log likelihood with the scalar lambda, right, then that allows you not to satisfy the Bartlett condition. But so by using a power likelihood, you relax that Bartlett condition where the variance of the scores and the expectation of the second derivative, that's the same thing. You relax that, essentially here. If you multiply with the lambda in front, then you get lambda times your Hessian, whereas you get lambda squared times this one. And then you have lambda and lambda squared. So it will be, you will get lambda times this and lambda squared times this one. And that's all, then that's only the same if lambda is 1. For any other lambda, it will be lambda times this, lambda squared times this one. It's no longer equal. So by introducing that lambda, it allows you to violate that Bartlett identity, essentially. Anyway.
Okay, cool. And recently, we've been working on parameter estimation for stochastic differential equations. Usually they're kind of small systems, and you can solve the likelihood through any optimization method, and it's fairly easy. But and also in your paper, you have these toy examples, which, you know, obvious because they have to be interpretable. But if you have if you're trying to have these crazy likelihood functions, and you have a huge system, let's say like 10,000 parameters, is it still possible to work with that, or not really anymore?
Yeah, if you have 10,000 parameters and you want to determine your I don't know how you do inference, but let's say you know your maximum likelihood or MAP solution, then you need to that the first derivative, 10,000 parameters, that's still doable more or less. But your Hessian or your sensitivity matrix, it's going to be computationally, you probably need to do a lot of additional runs to determine those two matrices, but you certainly can do that correction. Yeah, you can compute those two matrices if you know your.
But what about maximizing the likelihood itself? I know it's not quite in line with your paper, but I'm just curious, like how you.
So what type of model is this?
It's stochastic differential equation, and we're trying to estimate the parameters from different trajectories.
Okay. How many data? You have N is large?
And can be large, yeah.
Okay. Um, and how long does one model run take?
Uh, I'm more asking about the optimization itself because even when I've experimented a little bit with this, even when I'm doing kind of a not or 18 parameter system, let's say,
Yeah.
um, it the optimization seems really difficult. I don't know if I'm just not doing running the code correctly or
But what type of optimization method are you using? Gradient descent, Levenberg-Marquardt? What are you using?
uh
Broiden,
BFGS was the standard one.
Broiden, Fletcher? No. Yeah, I wouldn't necessarily do that with 18. If you use MCMC, and again, that's why I ask how long does it take to do one run? Because 18 parameters with MCMC, if your model requires less than a minute to run, you can solve that easily. And then you have no problems that you now experience because you have a stochastic problem. And then with Broyd Fletcher, with the gradient descent method, that's really going to cause problems because your gradient may be very well defined at a given point, but because you have a stochastic problem, the question is, what is that gradient really worth at the specific point? So that's where you need MCMC type methods that traverse that landscape much easier.
Yeah, makes sense.
So yeah, I do a lot of teaching on these methods. I'm writing a book. It's part of my book, all these methods. So I've played with them, and we're now correcting them, by the way, because if you look in Gradient, Broyd and Fletcher, there's another algorithm. There's two ways of getting your feature information, and that's exactly A and B matrix that are messed up in the literature, either the variance of the scores or the second derivative of the log likelihood. But they're used interchangeably, and people don't realize that. Anyway, it's very all closely related to misspecification, but yeah, I would not recommend using a gradient-based method, but try an MCMC type method. They're designed because they sample the distribution and much easier solve those type of problems.
Uh, Great, thanks. Vince, do you have any questions?
Yeah, thanks for the talk, Jasper.
You're welcome.
I have a question. It's more, I probably just missed this a little bit. So, yeah, follow the simple example where you have misspecification for a Gaussian and a uniform. So you mentioned like the parameters are just misaligned. They're just different parameter spaces. But that's for a random variable in one dimension. For a time series parameter estimation problem, uh, I was wondering if you could give a bit more intuition on what it means, I guess in general, to be misspecified. I know that for a hydrology example, you had some parameters A, B, and C, but I didn't really catch what they were.
Yeah, so it is a good point. Let me say something here. I skipped that about because this I think relates to here bias and variance. Okay, just as a side note, so you can ask yourself, so it's without doubt that that sandwich estimator gives you a robust description of the variance. That's without doubt. But the fundamental question is, what is the use of having a robust estimate of the variance if the estimate, a parameter value, is meaningless? Right? Because that's what we're talking about. What is now the meaning of a parameter when the model is misspecified? And so, yeah, that's a good question. So in the case study, and I can't answer that, that is really model dependent. In the case study that I use with ABC, here, so, so we have A and B. So here's a table. A is the fraction of precipitation that becomes surface runoff. So in this, A times P is this one. Then B is the fraction of infiltrated water. So likely I is B times P, I guess. and then, or something related. And then C is the fraction of groundwater storage that becomes base flow. So this flux is C times its storage value. So those are the parameters.
Those
And
are
this,
the parameters. But what about, I would have figured that misspecification would mean that the functional relationships that you're assuming are not correct.
yes, you're right. And in this case, the way I introduce misspecification is just by perturbing the rainfall. So we still use the correct model, but with the wrong rainfall.
Okay.
And that I do that so that we can do this analytically. But fundamentally, you can have a perfect model, but if you feed the wrong input, we cannot distinguish between those two. Both are misspecification. So wrong rainfall on a perfect model is a misspecified model. Even though the model is perfect, but we can't see those differences. It's impossible to differentiate between those two, unless you have a lot of information, alternative sources of rainfall, right? That you can benchmark your rainfall. Other than that, it's the same thing.
That makes
In
sense.
this example, the misspecification was the multiplicative versus additive noise, right?
Yeah, so what I did is, after I created some synthetic time series with values of fixed values A, B, and C, I think they're listed here. Let's see here. Here we simulate a 5-year record using these values. I then add some heteroscedastic error to those values using this relationship. So my measured values are synthetically generated with these values of A, B, and C. And then in the first step, I use that record to determine my parameters again. So what will come out is, these are my maximum likelihood values then, because those were used to create the data in the first place. And you see A and B are the same thing. Then what I do, I still use the same data synthetically generated, but now what I do during inference, I corrupt my rainfall record. So I suddenly introduce an error in my rainfall record. By adding 25% error. So if rainfall is 100 millimeters a day, it's now between 75 to 125. And I do that every single day. So the model is still the same. It's just that the rainfall I'm using is the wrong rainfall. And the effect is already noticeable here. So if you extend this to the real application, in the real application, you have your rainfall error and you have your model. So it's a further model error on top of that.
Do you have any examples? So in this case, it's imperfect measurement causing misspecification. Do you have examples of perfect measurement but incorrect model? And then you explore kind of the asymptotic, what do you call it, scores?
That's a good point. I actually did that. It's not part of this paper. So what I did is, it's actually funny. Let me see here quickly. So I think it's, so a number of years ago, I suddenly got involved in a project. And anyway, it's a long story, but so I worked a little bit on infiltration, and there is this 3-parameter infiltration equation of Parlange, 1982. People don't know how to solve this because it's a semi-implicit solution. You have infiltration on the left side and on the right side. So you get something that is x is the cosine of x. What is now the root? So in this paper, I show how you should solve this using Newton's method and show how that works, all the steps, and how that root is really when you go to the secant method. So the point is, you can generate cumulative infiltration data with this 3-parameter model and then fit it back using that 2-parameter model. So then you have the right boundary conditions, because it has those models don't have input, it's just a curve. Yeah, time is an input. Okay, that's fine. But you have the wrong model because you use that Parlange 3-parameter model to create the cumulative infiltration. I should go this one. You use the Parlange to create, and then you use that 2-parameter formulation to infer the parameters. I have done that, yeah. And you do see, depending on the type of data, that the model is misspecified. So you clearly see the effect on the parameter estimates. Let me see here, where is that 2-parameter formulation of here? This one. So I can create data with another infiltration model. So then you really have a model error.
I see.
Yeah, so I've done that study. Here it is. This is another infiltration model. You can generate cumulative infiltration with this and then use this one. And then do all the math. But the problem with that is, Vincent, is that, yes, the sandwich is slightly different, larger, but I mean, that is what comes out. I have no other way of benchmarking that. But that's a case study. It was certainly work that is just not part of this paper, but it's a study that can be done. Yeah.
Yeah, that's fair. I don't know. I'm interested in the problem of like a lot of these parameter estimation techniques, you first assume you know the model. So you know kind of how the noise is modeled, you know roughly the functional relationship and how the response is changing with respect to the input. But yeah, just a greater question is, okay, if you don't know this, yeah, like can you first detect what the relationship is? Maybe first by, I guess, some score-based method was something I was looking at or thinking about. But yeah, it's
No. Yeah, I never. So basically, you're saying you don't have the model yet.
yeah, exactly.
So why? But that sounds like a typical machine learning type of, just an ANN, artificial neural network, and all that to get some ideas about the functional relationship. But yeah, you're not really getting the functional relationships there.
Yeah, still, I don't know. It's a pretty new question I've been thinking of, but I don't know. I see some links. I have another question too. I don't think it's super related. You mentioned how if there's model misspecification, one of the key identities, I can't remember what the name is, but it's something about the expected variance or of the score. Where is it? Um,
Bartlett identity.
yeah, yeah. So you mentioned that the Bartlett identity fails when you have misspecification. Is this like a if and only if? Is the definition of misspecification about the Bartlett?
Yes, yes. By definition, that will fail. Yeah,
Okay, and it goes both ways.
yeah.
Okay, interesting. Yeah, I never heard of this, but this is very interesting.
Now I have to be careful there. So if your model is misspecified, this identity will not be true. If this identity is not true, is your model then misspecified? This goes back to our earlier discussion. What is your definition of misspecification? You can have the perfect model, but fed with the wrong rainfall, say, right?
Right.
So, but in general, yes, it is true. It just depends on what is your definition of misspecification, because that's also, again, you can have the perfect model with the wrong rainfall. Is that a misspecified model? The answer right now is yes, that's a misspecified model.
Would the Bartlett, yeah, the Bartlett identity would fail in that case, right?
Yes, yeah. And the essentially, when I came across this, a lot of things that I read in the past suddenly started making sense. If you look up, you'll see that in papers, people use definition of the Fisher information, and you'll see that they alternate. Some people present this definition of the Fisher information, other authors present this definition of the feature information. The feature information, in strictest sense, is the variance of your scores, of your first derivative. That is the strictly formal definition of the feature information. So I'm making some corrections still, but that is how it should be defined. Look at the Wikipedia. A lot of people also define feature information like this. And they're the same. If your model is correctly specified, then it doesn't matter. It starts to matter when your model is misspecified. And we're always working in that case. But, I mean, in applied sciences, we have a time series, right? We have some model, and we're always misspecified.
Right.
And so everything started, it's the same with, I worked on Jacobian or gradient-based methods a lot. And when I started studying theory, people talk about the Jacobian matrix. But you have two types of Jacobian. You have a Jacobian of your function, but you also have a Jacobian of the residual, and they're negatively related to each other. Now, in most derivations, that's absolutely not clear. I call it when I teach, I call it JF is Jacobian of the function, and J epsilon is the Jacobian of the residual. But in most papers, that distinction is not made. Gradient-based methods, some approximate that Hessian matrix this way, some approximate it this way. But that distinction is not made. And so essentially, that's all based on misspecification. It all doesn't matter when your model is correctly specified. Then it's all the same thing. It starts to matter when it's misspecified. So Broyd and Fletcher, they do a prediction of your Hessian, right? The second derivative. Based on your current estimates and the cost function, so you don't have to recompute it at every single step. It's computationally, but I think that's based on this one and not this one. Anyway, yeah, I hope it wasn't too technical. My interests are in getting the theory right and the application. I know that most people in the applied fields, they only care about the result, not so much about the theory beneath it. So.
No, Vincent loves theory, so it's perfect.
Yeah, it's becoming more of a struggle. Also in this paper, it's 80 pages, and I have a lot of derivations because I've been teaching now for 20 years or so in summer courses, and students love to have explanation. That's always what they tell me, that in a lot of papers, they miss key steps that they cannot redo because they miss that information. And they love these databases, or they love to have all the information there, essentially. And those are the people that I write for, essentially. But I'm always reminded by reviewers, and they say, we just trust that you know that you know what you're doing. In other words, I take all this time to get to this difference in the Fisher and Kodem information, whereas I could have stated that in one equation or two equations. This is the end result, and we'll move forward with that, right? But you're just trying to show the reader the beauty of all this. And once you understand this, a whole world opens up, right? Then you can, but yeah, I don't know.
Yeah, the group you presented to was just math people who have some interest in hydrology and some hydrologists who love math. So it's perfect amount of theory. Thank you.
I appreciate that. It's I think in general, take home point here, in everything we do, and believe it, I teach all this stuff MCMC, and even in MCMC, that's why it goes to the effect. There is an assumption that your model is correctly specified. That's already in Bayes law, essentially. And people apply that, but don't even realize it, right? So basically, my take-home message for you guys would be, just in general to anyone, is think deeply about it, that in all the methods you use, statistical methods, hypothesis testing, there is an implicit assumption that your model is part of that the correct model is the model you're using, essentially. It's part of the model space that you're working in. If you relax that assumption, a lot of these statistical tests no longer give you the correct answer. And that is what's going to happen in the coming years. People are going to realize this more and more. And then standard methods that we've been using for 100 years are no longer giving you the right answer, so to say.
Yeah, I mean, that's basically what my entire thesis is about, because, I see that, hydrology has very special data. There's a lot of assumption breaking properties within it. So I think hydrology needs a big update in the statistical methods it uses and machine learning and stuff. Just one last question about the K. The K part was very interesting. So what do you need to calculate K? Can you just calculate it given a guess for the model structure and data, or do you need like the ground truth data generating process as well?
No. So what the K is a measure, let me pull up those A and B matrices. So K is one measure of the conflict between the A and the B matrices, A and beta. So A is the sensitivity, so that's the second derivative. This is the variance of the first derivative. So you need your maximum likelihood solution, parameter values, you create a simulation, then you compute your Jacobian matrix, and you compute your Hessian matrix. To do so, you don't need to do anything analytical. You have numerical estimators of Jacobian and Hessian, robust ones. You can standard recipes. They will give you Jacobian Hessian matrix. Once you have your Jacobian, you have your A matrix, or you have your B matrix, because your B matrix is Jacobian prime times Jacobian or so. Then you have your B matrix. And then you may have to correct for autocorrelation. That's all in the Jacobian matrix. All the information you need to do the correction is in that Jacobian matrix. Okay? Once you have your A and your B, then you can compute that K value, which is just, I think I write it out here. Here. It's the number of parameters you're estimating divided by the trace of beta times inverse of A. That's your K value. So if beta and A are the same thing, K is 1.
Yeah.
The more
I think
different
that's great. I mean, I've seen so many papers about, I think they're trying to get at this, but they do it in kind of a, not theoretically justified way. And I've even had questions in my lab about it as well. So I think that K is, really important to communicate to hydrologists.
But the only thing is that this assumes that the eigenvalues are equal to 1, meaning the K value is in fact, you should have a K value for every single parameter. If you want to really preserve all the information in A and B and how different that is, you have a K value for each dimension. And that was what my conversation with my colleague was about. We now found a way to do that. We then, in a theoretic way, to do that correction. Then we found a way how to change the Metropolis algorithm to account for that, and then converge to the sandwich variance. And that was exactly about this, because K is just a geometric mean. In fact, each parameter, because that A and B matrix, that's it. Those are both D by D matrices, right? It is D square values in that matrix, so half of which are the same about, but okay. But you cannot represent that disagreement of those two matrices in one scalar unless they're perfectly quadratic. Then you can. But in most cases, you can. So you should estimate the K value for each individual parameter. You can take a mean value. This is the scalar approach, but this is not perfect yet, but it's getting there. This is the easiest to compute. But so the next papers we write on this are really for statistical journals, okay? But that will carry over. But this is a good start. What I found so counterintuitive that under misspecification, your uncertainty is no longer dependent on that lambda, essentially. It just drops out. Okay? So clue method has always raised that likelihood to some power to inflate, to make the likelihood more flatter, to disperse the uncertainty. And point is, in theory, that does nothing to your parameter uncertainty because that lambda cancels. And why did we always do that? Because the theory suggests that if the model is correctly specified, then it matters according to theory, because then you get lambda times your feature information, then it matters. But under misspecification, lambda cancels. So that whole clue idea, I talked to Keith about it, Keith Bevan. I said, hey, did you know it is completely based on a misconception? Because parameter uncertainty does not depend on that lambda or k for that matter in the misspecification. Anyway, there's more to do. There's a lot of theoretical things that have not been figured out yet. There is an inconsistency here between frequentist and Bayesian approaches. So we're trying to work on that.
Awesome. Thank you. Vince, anything else?
Yeah, I have one last question if you don't mind.
Yeah. I have a few more minutes, but then sorry for going over time.
Oh, that's all good. I thought it was interesting. So okay. I think that a result is a hypothesis is that if you have a properly specified model, then MLE estimators are consistent. Is that true?
Yeah, but they're always consistent.
Oh, even if you have a misspecified model?
Yeah, they're always consistent.
Oh, okay. I guess, I don't know, maybe I just don't understand some of these things. I would have thought that if you didn't even have the right, if you didn't even have the right parameter space, there's no way they can have consistency. But
you converge to the correct parameter values under misspecification, but those are not the parameters of the data generating process. So let's see here. So to know the animal is actually in the case of a misspecified model, a law of large numbers. Okay, we should not write instead we should that. Okay, so theta naught were the parameter values of the data generating process. We cannot estimate those under misspecification. So instead we estimate theta star. So under misspecification, the true parameter lie in a different space than the parameters that we use in our model.
right.
The true parameters are theta naught. Then under misspecification, the closest we can get to is theta star. And the maximum likelihood estimator is consistent, meaning that when n goes to infinity, our estimated parameters, the head theta hat n, they will approximate theta star. They will converge to theta star.
Got it. Is theta star equal theta naught if you have properly specified?
Yes.
Okay.
Yes.
Perfect.
Yeah.
Yeah, that clarifies some things.
So another thing actually I have to think about next, what this also implies for information theory with Shannon entropy and all that. Whether that's all still true in the misspecification. Anyway, that's another thing as a next step. Because I want to relate that Codamba and feature information to Shannon entropy. Because I
we
think
all
there's
love
also
information theory over here as well. It's interesting.
So, yeah. Anything else?
That's it for me. Thanks again
Yeah.
for the talk.
Oh, you're welcome.
Thanks. Do you want me to